Thanks for the introduction. So hi everyone, my name is Mingyu, and today I'm going to present Ditto, an end-to-end application cloning framework for network cloud services. And this is a joint work with Meta and Intel. So first, let me give you a one-slide summary of this talk. So the lack of representative and open source cloud services has been a long-standing problem for the architecture and system research. And generating synthetic benchmarks through performance cloning is a promising solution. But however, existing work is limited to CPU-centric, user-level, and single-node services, which is not enough to capture the complex behavior of cloud services. So in this talk, we propose Ditto, an end-to-end cloning framework for cloud services. So it is the first system to clone an application's behavior across the full system stack. And it targets both monolithic and multi-tier microservices and can generalize across platforms, loads, and deployment configurations without retraining. So cloud computing nowadays hosts a large fraction of world's computation, ranging from the machine learning workload to the latency-critical interactive services. And studying these applications is imperative to correctly design the system that populates the future cloud infrastructure. And there are three approaches to performing these studies. So first, using the real production services is naturally the most representative approach, but they are rarely publicly available, and open source applications often lack the complexity and update speed of a real cloud deployment. And studies rely on simulations or repeating traces offer some representativeness, but they are often tied to the system configuration when the trace was collected, and cannot easily generalize to arbitrary studies. And finally, generating synthetic benchmarks offers a middle ground with a synthetic benchmark capturing the critical features of the original service, but being malleable enough to adapt to different studies. So previous work on performance cloning profile the architecture in dependent features and generate proxy benchmarks to mimic their low-level CPU metrics, like the IPC and cache miss rate. But this is not sufficient enough to fully reflect the complex behavior of cloud services. So first, they only consider the performance metrics in user space, but nowadays cloud applications spend a large fraction of their execution at kernel level. And second, cloud services are often bottlenecked by off-CPU events, such as context switching, network, and disk I/O. And also, cloud services don't operate like independent processes. They have the network interfaces for communication. And this is even more the case for the multi-tier microservices, which can have hundreds of dependent tiers and are becoming the norm in the application design. And finally, cloud services are often deployed in containers and co-located with other services, which can add different levels of performance overhead. And to address those issues, Ditto adheres to the following design principles. So first, it implements a full system stack modeling to capture not only the CPU metrics, but also the resource and application level performance metrics like network bandwidth, latency, and throughput. And second, it uses platform-independent features to ensure that the generated services are portable across platforms without reprofiling. And third, Ditto doesn't disclose the implementation of the original service. Application-specific characteristics, including the user space function calls, memory accesses, and application input are also concealed. And finally, we automate the profiling and generation process. Users are not required to have the expertise of the service to use this cloning framework. And this figure shows an overview of Ditto's cloning framework. So first, if the original application uses microservices, it will profile its RPC dependency graph and generate a set of empty microservices with the same topology. And in step 2, it profiles the application's network and thread model to generate the application skeleton. And then it generates the request handler with user-level assembly code and system call as the application body. And finally, it implements a fine-tuning to calibrate the output of the previous steps. And in the next following slides, we will describe in detail for each of these steps. So first, A topology of microservices is a directed cyclic graph, where the nodes are the microservices and the edges indicates the data flow between the services. And to capture this topology, we leverage the distributed tracing framework present in most production deployments like Jigger and Zipkin to identify the dependency graph of the tiers. And then based on the profile dependency graph, we generate a set of interconnected microservices with an empty request handler. And currently, we support two commonly used RPC frameworks, Swift and gRPC. And next, we define the application skeleton as a network and thread model of a service. So the network model describes how an application communicates with other services. So when acting as a client, it can, in synchronous mode, the thread will block on the network I/O to await responses. And for the asynchronous mode, responses are typically handled by specific threads via the callback functions. And similarly, on the server side, there are three common options: blocking, non-blocking, and I/O multiplexing. And the thread model describes how tasks are scheduled and handled by different threads. So in this example, it can be either the network thread to do the inline request handling, or to dispatch the handling to a dedicated worker thread. And to figure out the thread model of an application, we need to consider the functionality and lifecycle of different thread and thread pools. So to do so, we first use system tab to probe the network-related system calls and data structures to determine its network model. And for the thread model, we also use system tab to capture the user space call stacks as well as the system calls. So we will build the call graph for each thread and group them using hierarchical clustering to analyze the thread pool and functionality. And we will also monitor the event notification functions in both kernel and user space to identify the trigger point of the threads. And after we understand this network and thread model, we can configure the RPC framework parameters for microservices or generate a skeleton for single-tier services with predefined template. And next, we generate the application bodies through the dynamic profiling. So first, to capture the inherent CPU characteristics, we will model its instruction mix, branch behavior, memory access pattern, as well as the data dependency. And we will also profile the system calls with their count and arguments so that we can clone the kernel-level behavior and the device usage. And these profiling results will help us to generate the assembly code and system calls, which will be fed into the request handler of the synthetic benchmark to mimic the on-CPU and off-CPU behavior. And finally, Ditto implements fine-tuning to calibrate the output of the previous steps. So we follow a feedback-based heuristic to perform the tuning. So first, we can get the initial input from the profiling and feed it to the code generator. So we then generate the synthetic applications and run it on a specific platform to collect the performance metrics. And next, we will compare this data with that of the original service to compute the error and adjust the input accordingly. And we will repeat these steps until the performance converges. And to validate the accuracy of Ditto, we use a set of cloud services, including both single-tier applications and multi-tier microservices. And we validate Ditto on heterogeneous cluster with three types of servers. So first, we validate the accuracy of Ditto under different input loads. So in this readout plot, we compare the architectural metrics of memcached and its synthetic benchmark under the medium load. So the red area represents the synthetic application, and the blue area underneath represents the original. And the large overlap here indicates the high accuracy of the synthetic benchmark. And we extend this to the low load and high load. We can find the synthetic benchmark can closely capture and match the performance change of the original, even though we only profile under the medium load. And the accuracy is similar for other services. And additionally, we also collect the latency, and it shows that the synthetic benchmark can clone not only the low-level CPU metrics, but also the high-level application-level metrics like the tail latency and throughput. And similarly, we test the data across different platforms. So each of the application is profiled only on platform A, but validated on platform A, B, and C. And these data plots show that the synthetic benchmark can react to the platform changes in a similar way to the original application. And similarly for the latency. So in general, the fact that the synthetic applications can match the performance change on different platforms without reprofiling demonstrates that Ditto can accurately capture the critical and platform-independent features of the target applications. And Ditto has many components to model an application's behavior. And here we use MongoDB as an example to break down Ditto's accuracy. So we start with the simplest version where we only generate the application skeleton. And then we inject system calls and user-level instructions to match the total instruction count. And at this point, we can still observe the gap between the target performance. And next, we incorporate the branch behavior, instruction, and data memory access pattern, as well as the data dependency. So we can find the performance gradually converge to the target. And finally, we perform the fine-tuning, which calibrates the profiling errors and further improves the accuracy. So in summary, it's challenging but necessary to clone the performance of cloud services across the whole system stack. So we propose Ditto, an automated cloning framework for end-to-end cloud services. So it first generates a microservice topology with an RPC dependency graph and generates the skeletons through the network and thread modeling. And finally, it generates an application body with the system calls and user-level assembly to mimic the on-CPU and off-CPU behavior. And we conduct a comprehensive evaluation with a diverse set of single and multi-tier microservices. And the results show that the synthetic benchmarks can accurately capture both the low-level and high-level performance metrics, and it's portable across platforms, loads, and deployments. So as for future work, we plan to extend Ditto to support more domain-specific workloads like machine learning models and specialized hardware like GPU and FPGA. So finally, we open source the Ditto. Feel free to take a try, and any feedbacks are appreciated. Thanks again for the listening. Questions are welcome.